In this short video, I'll discuss the following topics. Topic number 1, two-sided versus one-sided test. Topic number 2, 3 decision rule for hypothesis testing. I'm going to use two-sided test as an example. Rule number 1, range rule. Rule number 2, distance rule. Rule number 3, shaded area rule. So I'll give some simple name, easy to remember. Topic number 3, relate to the Excel function for the above 3 rules. Topic number 4, a few in-class exercise. Topic number 5, one-sided test. First, so let's discuss the two-sided test. Okay. Suppose we calculate the mean and our hypothesis is, so this is our hypothesis. Okay. So our hypothesis is our mean equals x0. Okay. Our now hypothesis is x is not equal to x0. Okay. And for this one, so actually we have 2 ways to reject it. The first one is the mean is higher than or equal to x0. Alternative is, so this is x0. So we have 2 ways. Okay. And I'm going to draw a graph. Okay, so this is some kind of density function. Okay, this is density function. So this is our hypothesis. Okay, if we are given alpha, okay, alpha, and so actually we have 2 tail. So 2 tail. So this is half alpha, and this is another half alpha. Okay, so this is 1 minus alpha. So if our mean is inside this left tail or right tail, we reject. So this is called two-sided. Okay, so let's look at the one-sided. Okay, so our hypothesis is larger than or equal to x0. Okay, and then we alternative hypothesis is not true. So this is for one-sided test, we draw a similar distribution. Okay, so this is a certain distribution. Sorry for the ugly shape. Okay, so this is x0. Okay, and our objective is, so our hypothesis is mean is larger than this one. So this is alpha. So this is alpha. Okay, so this area is 1 minus alpha. So everything including goes in positive infinity. So this is positive infinity. So this is two-sided test, the graph. This is one-sided test, another graph. Okay, so let's look at the 3 simple decision rule. Okay, again, so let's assume this is two-sided test. So let's draw a, so this is let's draw a density distribution. Okay, so this is density distribution. And so this is our, okay, I'm going to write hypothesis. Okay, so this is x mean equals x0. So this is our now hypothesis. Okay, and so we know we have alpha. So this is alpha. So this is area is half alpha. And for the right hand side, we have another half alpha. So this is 1 minus alpha. Okay, suppose alpha is 5%. Suppose this is alpha equals 5%. Then this is 2.5%. This is another 2.5%. So this area is 95%. Okay, so the first rule I called range. It's a range rule. Okay, the concept is very, very simple. So if inside the range, we accept. We accept null hypothesis. Otherwise, we reject. So outside, we reject. Yeah. And it is obvious, right? Suppose we are given the text. Suppose xy is here, it's so close to x0, and inside the range we accept. It's here, it's here, it's here. If it's here, then we reject. Okay, the first range rule is easy to understand because it's inside the range, we accept. Okay. The second one, I call the distance. Okay, this distance rule. Okay. The distance rule is, okay, we know from the previous one, so this is, so from here to here, like this is our margin of error, right? So this is our margin of error. Okay, this is also true, margin of error. Okay, so let's call this distance with A. So this margin of error is B. Okay, if A less than B, accept. Obviously, right? For this x bar, this is A is shorter than this B. So distance rule is if A is less than margin of error, is B, accept. If A is higher than B, reject. Okay. So reject, right? Obviously, this is it's consistent with rule number 1, range rule. Okay. So number 3, I called shaded area. Shaded area rule. Okay. So I'm going to draw another one to make it a little bit clear. So this is, I'm going to draw it again. It's quite similar. So this is x0. And so this is half alpha. This is another half alpha. Okay. So let's, actually, the half alpha represent this area. Okay. Half alpha actually is from infinity. So actually from infinity up to here. So this is lower bound. So this is lower bound. So half alpha actually is area. Okay. A. So actually is probability, right? It's probability. From negative infinity up to here. Okay. So let's assume our x bar is here. Okay. X bar is here. Okay. So then if we calculate shaded area, it should be this area. I'm going to use this curve. So this area. Okay. Actually it's from infinity up to here. Of course this area is bigger than half alpha. So actually is, so if shaded area, if larger than alpha, accept. Otherwise, reject. And later, you will see, so this area actually is p-value. Actually, it's p-value. Okay. Okay, I'm going to repeat this concept. Okay. So actually, for two-sided test, okay, so this is for the two-sided test. Okay, it's two-sided test, and we have left tail. We have the left tail. We also have the right tail. Okay, so left tail is half alpha, and right tail is half alpha. Middle, this is we call the confidence interval, right? It's 1 minus alpha. Okay, the range rule states if our x bar inside this range, this confidence interval, we accept the null hypothesis. Otherwise, we reject. Okay, we accept the null hypothesis, otherwise reject. Okay. The distance rule states, so if the distance between our mean and our target value is less than margin of error, we accept. Actually, it means it's inside the range, we accept. Otherwise, we reject. The last rule is shaded area. So actually it's probability. Okay. And I use the left tail as an example. Okay. Suppose our mean inside the range, the shaded area will be larger than half alpha if you look at the left hand side. Of course, because it's symmetric, on the right hand side is also large. So actually, if our shaded area is larger than alpha, we accept. Otherwise, we reject. So these are 3 rules or decision rules.
Shutterstock Music.
Next, so let's conduct a hypothesis test for a two-sided test. Okay, so let's type that dot ICE, type dot ICE in class exercise. Okay, so this is two-sided test, golf test. Okay, this up arrow key, we got dot ICE, we enter 40. Okay, so these are explanations, and I'm going to copy to this part. And also there are 3 ways to get the data. Okay, I'm going to use the first one, dot A, I'll search golf. Okay, so this is ID, so this is chapter 9. So data ID 137, then you dot B 137. Then I copy the dataset to Excel. Alternatively, you can go to this web page to download the CSV file, or go to this web page to download the TXT file. Okay. And method 1 is excellent for the Windows user. And for the Mac user, you can method 2 or method 3. I'm going to use method 1. A, golf. Okay. So this is 137.b, B137. Okay, this is the launch Excel and paste. So I choose A1, so I paste it here. Okay, so actually only column A is meaningful. Okay, so this is we have assumption is mean equal to 95. Okay, so this is our x0. Okay. x0 is 295. Okay, I'm going to make it bigger. Okay, it's 295, and standard deviation is given is 12. Okay, so if standard deviation is given, then we calculate z. Okay, so sigma is given. If standard deviation is not given, then we apply t. So this is normal distribution. This is t distribution. Okay, to calculate this is actually the distance. We apply 2 methods. One is I call the distance. Okay, distance. Because sigma is given, we calculate z value. Okay, so this is we calculate mean, and we calculate n. So this is count. Okay, okay. Mean we use equal average. So this is equal average. Highlight, Control Shift down. Okay, and close it. So this is our average. Okay, I'm going to use formula text to show the formula. Make it bigger. this is then we calculate mean. Okay, and we can repeat the same times, same procedure for the standard deviation. A better way is we log the cell. So if you look at here, $A, $2, $8, $51. I simply copy it. So instead of average, I can use count. Okay, so this is count. Okay, so this is count. Okay, so alpha is 5%. So alpha is 5%. Okay. Okay, so let's assume this is called A. So this is called B. Okay. So A equals our mean minus our hypothesis. Okay. So this is our mean minus our hypothesis. So this is mean minus our hypothesis. Okay, it's the difference. Numerator is difference. Okay, so the B. So B actually is standard error. It's standard error. Okay, standard error. So equals given, because sigma is given, divided by square root of n. So square root of n. So this is B actually is denominator. I'm going to copy the formula. Okay, so this is the formula. Okay, so this is the difference. Okay, so what is the z value? So z value is the A divided by B. So this is z value. Okay, it's 1.56. So usually I use absolute z. Okay, I use absolute z. In this case, it is positive. It looks like redundant. Okay, this is absolute z value. Okay, I'm going to copy and show the formula. Okay. Okay, so let's look at the z critical. Because this is two-sided, so this is, we have to alpha divided by 2. So this equals norm S I N V. So this is norm F I N V. So this is should be 5% divided by 2. 5% divided by 2. So this is, I'm going to use the formula. You see the negative. So actually we compare z value with absolute critical value. Okay, so this is a decision rule. Okay. So I'm going to use absolute value here. Absolute z. Okay, just make it easy. So this is absolute. Okay. Obviously, because 1.53 is less than 1.95, we do not reject null hypothesis. So they are equal. So this is decision rule. Okay. If our z value is less than critical z value, we accept. Otherwise, we reject. Okay. So this is, I'm going to show the formula. Okay. Okay, so this is a decision rule. It's I call the distance. Okay. Decision number 2. So let's look at the p-value. Okay, so this is equals norm its distribution. So we look at x value. case of x value. So this is our x, actually is our z value. Okay, z value. And in this case, we should use, we don't use absolute z. Okay, so this is 1.5 z value. And we should choose standard normal because it's standardized. Okay, so this is mean 0. I'm going to use s dist. This is standard normal. So this is z value. Okay, and because this is right tail, so we have to use 1 minus. We have to use 1 minus this one. Okay, so this is very, very important. Okay, so if it's larger than mean, we have to use right tail. If it's less than mean, we use left tail. I repeat. Okay, if x bar larger than HO, use the right tail, i.e. 1 minus probability. If x bar less than H0, use the left tail, i.e. itself. Okay, so this is a very, very important principle. Okay. Okay, so this is P because it's one tail. It's actually it's half P. Okay, and so P equal P half P times 2. So finally, the P value will be this one times 2. Okay, so this is the decision rule. Okay, if P value is less than alpha, we reject, otherwise accept. Obviously, we accept. Okay, so this is, I'm going to copy the formula here. Okay. Okay, I'm going to summarize this exercise. Okay. For this exercise, we test a hypothesis. Our mean equals 295. So this is population mean. Okay. Our calculated result is 297.6. It's higher than this population mean. Okay. Because the standard deviation is given 12, then we use z value. If standard deviation is not given, then we simply use t. We calculate t. Okay. And to calculate the z value, we calculate a and b, numerator, denominator. Okay. So numerator will be mean minus our hypothesis. Okay. Denominator is standard error because standard deviation is given. Then we use standard deviation divided by square root of n. Then we calculate our z value. Okay. Because z value is positive, it suggests we have to use right tail. Okay. To calculate z critical value, and we use norm, S inverse, and alpha divided by 2. Why alpha divided by 2? Because it's two-sided test. Okay. So if we compare absolute, the z value is 1.53 and critical value is 1.96. Because z value is less than critical value, I'm talking about absolute value, we accept now hypothesis. Okay. When we apply the P and shaded error rule, P, okay, so we calculate P value. Okay. Because this x mean is higher than 295, we look at the right tail. And to calculate the right tail, we have 1 minus cumulative distribution. Okay. Because this is half P, then we have to times 2. So the P, probability, the shaded average 12.6%, is higher than 5%. We, according to the P value compared with the Z value, we also accept null hypothesis. Yes, they are equal. Next, we are going to have a one-sided test. Okay, just click cls.cls. No, ICE, in-class exercise. Okay, in-class exercise 41 is one-sided test. Coffee. Okay, so .ICE 41. Okay, so you can read this one. So basic idea is they claim a can of coffee contains 3 pounds, minimum 3 pounds. So this is assumption. Okay, this is assumption. So our hypothesis mean is higher than or equal to 3. Alternative hypothesis is less than 3. Okay, according to instruction here, so the standard deviation is 0.18 is given. Because the standard deviation is given, we apply the normal distribution, and alpha is 0.1. We have 3 ways to get our data. Okay, I'm going to use the first one. Okay, dot A, so type coffee. Okay, the ID is 133. Dot B 133. Then I'm going to use copy and paste to Excel. If you are a Mac user, you can go to this link to get a CSV file. Alternatively, you go to the next link, you'll get a text file. So I'll go to Excel, I put a question here, and we can calculate Z value if sigma is given. Alternatively, we calculate T value. If sigma is not given, we calculate ourselves. So let's launch Excel and we paste it. Okay, so we paste it here. Okay. So actually only B column matters. I'm going to delete all the other columns. Okay. Highlight, delete. Okay. So actually okay. And for this exercise, it's one-sided. Okay, so we are going to test whether your mean, sample mean is greater than or equal to 3. Okay, and sigma is given is 0.18, and alpha is 0.01. Okay, so SDE is given 0.18. Okay, the H null hypothesis is 3. Null hypothesis is 3, and alpha is 1%, 0.01. Okay, and we calculate our how many observation. We calculate the mean. We calculate Z value. We calculate absolute Z value, and we calculate Z. We calculate critical value, and use absolute Z critical. And then we use decision rule. Okay, decision rule number 1 and distance. So so distance is we calculate the Z value. We calculate Z value compare. This is all calculated Z value compared with the critical value. If it's less than critical value, we accept. Otherwise, we reject. Okay, this is decision rule number 1. So this is decision rule number 2. Okay, then we compare P versus alpha. Okay, P versus alpha. Okay, P versus alpha. Okay, so let's calculate the N. So N equals count. Okay, count. We highlight, Control Shift down, then we close it. So it's 36. I'm going to use formula. It's a formula to show the formula. Okay, I'll make it bigger. Okay. So instead, I can use the mean, do it again. I'm going to lock the starting data set and ending is B2, $B, $2, $B, $37. So I copy the formula. Okay. So instead of use count, I use average. So this is average. Okay, so this is average. Okay. And the Z value, I apply this formula. Okay. Again, it's a good idea. I simply calculate A and calculate B. So let's do it just once to see. So equal parentheses, the mean minus our hypothesis. Okay, divide by, okay, parentheses, don't forget this one. Standard deviation is given. Standard deviation divided by square root of n. So n is 36. Close it again. So this is our Z value. Okay, this is our Z value. Okay. So let's double check. Okay. Numerator will be our mean minus, so E7, our mean minus E3. E3 is given hypothesis. So this is E2 is standard deviation divided by square root of n. E6 should be n, correct? So this is correct. Okay. Then use absolute value. Okay. The textbook mentioned, if we don't consider the positive and negative value, and if it's negative, we compare with left tail. If positive, we compare with right tail. But I still prefer use distant. We always use absolute value. Okay. So let's look at, so I'm going to show the formula. And so this is absolute. Okay. Let's look at critical value. Log S. So this is inverse. Okay. So this is probability. So probability is 1%. Okay. Why we don't divide by 2? Because this is one-sided. Okay. So this is 2.33. So this is 2.33. 2.33. And so according to the textbook, negative, because it is smaller than this. And I use absolute value. I use absolute value because it's much easier to understand. The distance is always positive. So this is decision rule number 1. If our distance is less than absolute critical value, and so it's less, we know it's inside the range. It's less, accept. Otherwise, we reject. So we should see reject. Okay, so let's copy the formula here. Okay, so if our absolute value, so this is our absolute value, 2.66, is less than 2.33, we accept. Otherwise, reject. Because 2.6 is higher than 2.33, we reject. Okay, so according to the textbook, it used Z value compared with, so I'm going to textbook approach. Okay, the textbook approach is if with signs is less than negative critical value, we reject. Otherwise, we accept. Okay, also we got reject and reject. Okay, again, I prefer using my approach. Look at standard. So look at the absolute value. Okay, so let's look at decision number 2. Okay, decision number 2 is we calculate the p-value. Okay, So p-value. So what is p-value? So p-value, and p-value is we use norm, okay, and standard distribution, okay, standard distribution, and this is a z-value, okay. When we use z-value, because this is less than our hypothesis, then we use z, okay, so this is p-value, okay. So our decision rule, if the p-value is less than alpha, and we reject. And we reject. Otherwise, we accept. Okay, so this is, because this is outside the range, I'm going to copy these, show these two formulas. Okay, I repeat, just summarize this exercise. Okay, we have a data, and we want to test one-sided test. So one-sided test is mean is higher than or equal to 3. 3 is like, we can think about, this is assumption, this is population mean, and also we know standard deviation is given, and alpha significance level is 1%. Because standard deviation is given, we apply, we calculate z. If standard deviation is not given, we calculate the t-value. Okay. And I think the key is how to calculate z, how to use absolute value. So the z value is, we apply this formula. Okay. Then we compare the absolute z value with the absolute critical value. So if our value is less than critical value, we accept because inside the range. Outside, otherwise we reject. Okay, and it is also true when we apply another decision rule I call the shaded area. It's compared with the p-value with alpha value. If the p-value is less than alpha, we reject. So this is we reject. Otherwise, we accept. Okay, so we reject based on the distance rule, and also we reject based on when we compare the p-value and alpha.